we had the pleasure to introduce to Professor Platis. He told about quasi-conformal mapping with the Heisenberg Group. And
thank you very much. Good evening to everybody. I'd like to thank the organizers for giving me this splendid opportunity to talk about a context that I really am fond of. Well, the title of this talk is Quasi-Conformal Maps in the Heisenberg Group, an overview of the Koranyi-Reimann theory, some developments and some open problems. Of course, you must understand that this is entirely of personal flavor, and there are many other questions that will not be addressed into this talk. So it's going to be something like a summary of mine, and not, just some general thing. Okay, no. What I'm doing wrong? Oh, that's okay. So the talk will be 4 chapters. And the first chapter is Introduction and Motivation. Well, I happen to be very philosophical about motivation. What is motivation in mathematics? Why do you do mathematics? Well, the only reasonable answer in my book is because I like it. Okay? I mean, what is useful for? I don't know. Okay. The second, we are going to talk about a little bit about Heisenberg Group, so we get familiar with this group. In the third, we're going to overview the Koranyi-Reimann theory. And finally, we're going to talk briefly about further developments. Okay, so what is a quasi-conformal mapping? It is these gold letters above, okay? So a naive, not that naive answer is that in the complex plane, when you have a QC mapping, which was introduced by Grech and named by Alfors, between domains maps infinitesimal circles to infinitesimal ellipses, of which the eccentricity is bounded by a constant strictly less than 1. Okay, and it is the most neighboring mapping to a conformal mapping. But of course, people have written papers about what is exactly a quasi-conformal mapping. One can see a paper written by Labourie, which is very interesting. So when did this mapping appear? Well, from the time of Gauss, actually. Find isothermal coordinates in a surface. To do that, you have to solve the Beltrami equation. And this is not obvious. In the 20th century, we have the rising of the theory. And this was happened because of Grech, Lavrentiev, Alfors, between others. And we have extremal mappings, modular space of a Riemann surface, and this is due to Teichmüller. In the mid-20th century, the use of quasi-conformal mappings was to study Teichmüller spaces, and then it is a heavy use of what is called the Alfors-Baer theory. And people that have worked in this area, and they're still working, are so many that we need 2 hours just to name them. Okay, so why quasi-conformal mappings in the Heisenberg group? It all started from the proof of Mostow rigidity. So what is Mostow rigidity? We can write the statement like that. Suppose that we have M&M complete finite volume locally symmetric spaces of dimension n greater than 3. If there exists an isomorphism of their fundamental groups, then it is induced by a unique isometry from M to N. In other words, if you have a diffeomorphism, a homeomorphism, then it is an isometry, and in particular, it is a conformal mapping. Okay, this Mostow rigidity thing has serious consequences. 2 of them are that Teichmüller space is just a counterexample of this thing. To prove this, Mostow used something which is called absolutely continuity in measure, and this thing does not hold for quasi-symmetric mappings in the circle. And the second serious consequence is the rising of the quasi-conformal mappings of the Heisenberg group. Okay? The proof used quasi-conformal mappings in their own Riemannian setting. And besides this Koranyi-Reimann thing, which proved it in general, Pansy has proved an even stronger result known as Pansy's superrigidity theorem. In the quaternionic and the octonionic case, you cannot have quasi-conformal mappings. Quasi-conformal mappings are conformal. So the only interesting case is when the symmetric space, the symmetric space of rank 1, the hyperbolic space, is a complex hyperbolic space. And this phenomenon has not been explained yet. Okay, Heisenberg group. The Heisenberg group can be realized as the set C times R with a group law, this one. So you see, in the first coordinate, it's just addition of complex numbers. In the second coordinates, things get a little bit mixed up. You add the real numbers, but also you add the symplectic form of Z and W. Okay. Now here we have something that it's called the Koranyi gauge or the Heisenberg norm, or I don't know how many names it has been called. So it looks like a norm, but it's not. It is a gauge. So each point of the Heisenberg group, you assign this real number. So if you see, you have absolute value of Z to the squared, and you have T into the first power. From this gauge, we obtain the Heisenberg, Koranyi, Sigan, you name it, metric, which we shall denote by dH. And this can be defined in this way. Okay? Well, about this metric, some things. So this metric, it satisfies the triangle inequality, but it's not a path metric. Okay? Okay. So some things about Koranyi-Sigan metric. In the first place, we have the isometries. Isometries are left translations, which are defined like that. You have rotations about the vertical axis. It's just the action of U1 in the first coordinate. And you have an involution, which is orientation preserving, that takes ZT into Z bar minus T. All these guys are isometries of the Koranyi-Sigan metric. We have also similarities, and here we have the appearance of dilations. If you have a delta which is positive, then you define dilation delta of ZT equal to dZ, d square of T. And this is one of the significant differences between this metric and the Euclidean metric. Dilation in the Euclidean metric, you multiply its coordinate by delta, but here in the real coordinate, the multiplication is by d squared. So what happens to the metric is that it is scaled up to delta by the action of the dilation d delta. And finally, we have an inversion. We place the counterexample of the Euclidean inversion, which is defined like that. You see in the denominator is this gauge, in the inside of this gauge, which plays the role of modulus of Z to the squared. So the Heisenberg group is the prototype for contact and Subramanian geometry, and this because it is a two-step nilpotent Lie group. Its Lie algebra is spanned by the left invariant vector fields, these guys. X equals to d over dx plus 2y d over dt. Y equals d over dy minus 2x d over dt. And t equals to d over dt. Sometimes we use the complex vector fields instead of x and y. And take a look at these, because these play an important role into the Beltrami equation of a quasi-conformal mapping in the Heisenberg group. These are the analogs of d over dz bar, d over dz. Okay? And now we have the famous Bracken relations, first written by Heisenberg himself. So xt, yt is 0, but xy is minus 4t. That simply tells us that the distribution obtained by x and y is not integrable. It's what we call entirely not integrable. It is the prototype of Subramanian geometry. About the Haar measure being a nilpotent group is just a constant multiple of the Lebesgue measure in C times R. Now, the Heisenberg group has a natural contact structure, and the contact form is this one, dt plus 2x dy minus y dx, or if you want in complex terms, dt plus 2i imaginary part of z bar dz. So about this contact form, it is defined as the unique one form which satisfies the x and y's are in the kernel, and t is omega of t equal to 1. In other words, the t is the Reb vector field of the contact structure. Sorry. Uniqueness follows by the Darboux theorem, and the distribution, which we denote by h of h, a lot of h's here, right? H, we have RMH, we have a frac H, a lot of h's. X and y is called the horizontal distribution. Everything in the Heisenberg group is happening in the horizontal space. It's the only space that we care about. Okay, since we have a contact form, we can define contact transformation, and the definition of a contact transformation is this. So you have two domains in the Heisenberg group, then a diffeomorphism is contact if it satisfies this relation, f star of omega equal to lambda of omega for some non-vanishing real valued function lambda. Okay? In contrast with what happens in the Euclidean case, here contact transformations are very important in the Koranyi-Reimann theory of quasi-conformal mappings. It will prove themselves to be a huge obstacle in the resemblance of the theory to what is happening to the Euclidean case. So a contact transformation, it is equivalent to a system of PDEs, this one, indeterminate, which of course it's not easy to handle. One of the major problems to actually write a quasi-conformal mapping in the Heisenberg group is how on earth can you solve a system like that? I mean, perhaps somebody is an expert and sees it's peanuts. I don't. Okay? But this is the contact conditions, as we call them. Also, if f is C2, then the Jacobian matrix, the determinant equals to lambda squared, where lambda is the contact suffix. Okay. We have to talk about horizontal curves here. An absolutely continuous curve is horizontal if its derivative is in the horizontal space of the Heisenberg group. Okay? Now, this relation has several consequences. It is absolutely continuous with respect to the Heisenberg, to the Koranyi-Reimann metric. And this happens if and only if it is a horizontal curve. And also you can define the horizontal length of this curve by simply measuring the length of its projection to the complex plane. So it's one thing the length of a curve, and it's another thing the horizontal length. Okay? When you think about horizontal length, your curve is projected downstairs, and you just measure the Euclidean length of this projection. So you see it has a very nice expression with the x and y's. Now, these x and y's, we may define what we call a Subramanian product. According to this, xx, yy is 1 and xy is 0, and this is the essence of Subramanian geometry of the Heisenberg group. In Subramanian geometry, we have a metric which is called the Carnot-Carathodori metric. This is the distance of 2 points is taken as the infimum of the length of a horizontal curve which connects these 2 points. Well, a question here is obvious. When you have 2 points, can you find the horizontal length joining them? The answer is yes. And the roots of these things, believe it or not, were something like 100 years ago, when people were trying to understand the laws of thermodynamics. So it was this physicist Max Bohr who wrote a letter to Carathodori asking this question. In other words, so Carathodori just proved what I said that we can prove, and this was the beginning of Subramanian geometry. Now we have to stress here that the geodesics for the Carnot-Carathodori metric, Carnot-Carathodori distance, are the horizontal curves. Some things about the Carnot-Carathodori distance: the length of a horizontal curve is its horizontal length, because it's geodesic. DCC is invariant under left translation and rotations, and is also scaled up to the positive constant d under dilation d delta. And also, which is very, very important, there exists constants, so C1 dH of P0 is less than DCC of P0, it's less than C2 dH P0. That makes these two metrics equivalent. Okay, so let us enter into the main theme of this talk. So, quasi-conformal mappings. Well, quasi-conformal mappings, you can define quasi-conformal mappings in any metric space. You don't need to have any assumptions of smoothness, regularity, or whatever. Just have a metric space. So, quoting Koranyi and Martin-Reimann, the metric definition is a straightforward generalization of the corresponding notion in Euclidean space. And Mostow, for the first time, studied these mappings in the context of semi-simple Lie groups of rank 1. In the end of this talk, we will see that since Mostow, a lot of things have been improved. So what do we do when we have a space and we define quasi-conformal mappings? Well, we have for granted the metric definition, and then we're going to find an analytic definition. It's like, if you have a quasi-conformal mapping of the plane, first of all, we studied the smooth quasi-conformal mappings, but then it was obvious that such a mapping doesn't have to be smooth. So Alfors and all the others prove the equivalence of the metric definition, analytic definition, and so on. So we really want, from the metric definition, to go to an analytic definition that is equivalent, and then go to a geometric definition. And once we have done that, we can study the theory. Okay. So for the metric definition, we have all this mumbo-jumbo in the beginning, but it's not so crazy if you think about it. In the first case, we have a P in some domain in the Heisenberg group, and we take this LPR, which is supremum of dH of Fp, Fq. That is the supremum of the stretching from P. And we have this little l, which is the infimum of the shrinking from P. Stretching over shrinking, which is H, and then we take the limb sup. So, I mean, entirely abstractly, one can think of a quasi-conformal mapping like stretching over shrinking. So, a homeomorphism between domains is quasi-conformal if the essential supremum of this HP, let me show it again, is bounded, and it is called K quasi-conformal if there is a constant K such that it is bounded by that K. This is the metric definition, very abstract, and you see some easy things. We may substitute dH by the Carnot-Carothon metric, it makes no difference. But these two are quite important. Conformal mappings are one quasi-conformal. Conformal mappings are similarities of dH, and actually these are PU1. And the converse is always so true, and one quasi-conformal mapping is necessarily a Heisenberg similarity, I mean an element of PU1. Now, there is a big distinction between the Heisenberg group and the complex plane. In the complex plane, conformal mappings are all the holomorphic mappings. Here, only PU1, very few, compared to what happens into the complex plane. Okay, and now, going to the analytic definition, we give this strange definition of the Pansy derivation. Okay, as I write it here, it looks very, very strange. This is due to Pansy. God doesn't like Pansy, I guess. Pierre is a nice guy. He's the nicest guy I know. So, and it is due to Pansy, and he used this definition in the general context of Carnot groups. How do you define differentiability in a Carnot group? But let me explain. So, perhaps I need a chalk here. Okay. All right, so let us recall the definition of the derivative. Okay? Derivative in the real line. All right. So let me write it this way. Let me write this guy as follows. So delta to the 1 over c, that is translated by minus fx, that is the inverse of fx. And now, I mean, if you think that this is something that acts on some y, okay, or do it acting on c, this can be written again as taf f of x delta c. If you don't want to use c, use s, doesn't matter. So there is nothing strange behind this definition. It's just an obvious generalization of the usual derivative in R, which we all know and love. Okay? So let me read this. A mapping between domains of the Heisenberg group is P-differentiable if, for C tending to 0, these mappings converge locally uniformly to a homomorphism D0 of P from taf P to taf of P. And this preserves the horizontal space. This is very, very important. The horizontal space has to be preserved. Okay. There is a nice representation of the Pansy derivative, and you see the z guys appear acting on the complex coordinate of your mapping, zf1, z bar f1, zf1 bar, and zf1 all bar. You have very nice zeros, and there, in the end, you have the lambda. This guy, this difference of the squares of the absolute values is just the lambda of the mapping, of the contact mapping. You will see that later. Okay, and now you have the theorem due to Pierre. Quasi-conformal mappings between domains in H are almost everywhere p-differentiable. Starting from the metric definition, you get to this theorem. And this is in Pansu's thesis, 1974. In particular, if it is p-differentiable, now I'll explain in a bit, at some point of the Heisenberg group, and the derivative is d0, then the restriction to this plane, px of xx plus y is differentiable at p in the Euclidean sense. And its derivative is the restriction of d0 in horizontal spaces. In matrix form, it is given by this one, which is the upper corner of that previous mapping, that previous one. See that? It's the upper corner. Oops. Okay, so there is the Pansy derivative seen only in horizontal spaces, in horizontal planes. Okay. We have that the norm of this derivative is equal to zf1 plus z bar f1 in absolute values. Somebody who's familiar with quasi-conformal mappings of the plane will see the similarities here. Oh, oops. The determinant of the Jacobian is this guy. And we have this distortion function to the square, which is, you know, familiar thing from quasi-conformal mappings of the plane, but to the square, and this is less than k. So we have a square factor here that doesn't appear in the Euclidean sense, in the Euclidean case. Okay? This guy, kpf, is called the distortion function, and the constant of quasi-conformality is also called the maximal distortion. This is almost the same with what is happening in the quasi-conformal mappings of the complex plane. Okay. The basic property here is absolute continuity in lines. And it was the first thing that it happened to be an error in the first Mosto proof of Mosto rigidity. And it was Koranyi and Reimann that detected this error and altogether then fixed the whole thing. So absolute continuity in line means that mappings with this property are absolutely continuous on almost every fiber of any smooth horizontal fibration, in our case. Okay? And that means that the fibers can be parameterized by the flow of a horizontal unit vector field. So a horizontal unit vector field is a field of the form ax plus by, where a squared plus b squared is 1. Okay. So we have this theorem by Mosto. Quasi-conformal mappings are absolutely continuous on almost every fiber gamma of any given horizontal fibration gamma v. V is a horizontal vector field. I have a comment here. In the Euclidean case, this theorem was proved by Gehring. Mosto thought that the proof ran in the same lines here, but it's much, much more difficult. So that was the trick for Mosto rigidity in the general case. Okay, right now we have Pansy Derivation, we have absolutely continuous in lines, and now we have the Beltrami system. This is the counterpart of the Beltrami equation, and you see, it's not one equation, it's two. So we have a mapping F1 and F3. F1 is the complex coordinate and F3 is the real, but we also consider this mapping F2 Latin, which is F3 plus I of modulus of F1 to squared. And the Beltrami system is defined like this. It's not looking very good. I mean, it would be nice if you only had just one. I mean, if you only have the first one. But unfortunately, this is what happens. I mean, all these are like what happens in the complex case. We have Beltrami coefficient, and the Beltrami coefficient with a constant of quasi-conformality are related in the obvious manner, and so on. I don't want to get into details of that, but the analytic definition states that it's K quasi-conformal if all these three hold. It's almost continuous in lines, Pansy differentiable, satisfies the Beltrami system altogether. So this was the actual analytic definition of Koranyi-Reimann. Since then, a lot of analytic definitions appeared. Some of them are quite advanced and complicated, but if one is interested about that, he or she can consult the works of Darbekov, Heinonen, and Vodopianov, among others. So 3 things for the analytic definition. On? No? Yep. Okay, so I told you in the beginning that besides the analytic definition, we have a geometric definition. And why do we have that? Because to prove the equivalence of metric and analytic definition, Koranyi-Reimann didn't go straightforwardly from the one to the other. But they did this trick. They proved that both metric and analytic definition are equivalent to another definition, which they name metric definition. Okay? Geometric definition, excuse me. So I'm not going to show you here what is the geometric definition of Koranyi-Reimann exactly, but I will give you a similar one, which is probably most suitable for what I'm going to talk in the sequel. Okay? This definition will involve the notion of the modulus of families of horizontal curves. So, I mean, for anybody that's familiar with the modulus of curve of families, this will sound very familiar as well. So we have a rho, a non-negative Borel function, and a gamma, which is a parameterization of horizontal curve. Then we can define this line integral, but it's a line horizontal integral, because you see we have a norm with its horizontal length. It's gamma dot I. Okay? No? Yes. So we call adm of gamma is the admissible functions for gamma is these non-negative Borel functions which satisfies this inequality. Their horizontal line integral has to be greater than 1, greater or equal than 1. For all rectifiable gamma, we have seen that rectifiable is horizontal necessarily. So the modulus is defined as the infimum of this integral, this triple integral, rho to the 4th power with respect to the Lebesgue measure. Now, in the complex case, we don't have 4th power, but rather we have 2nd power. Another difference between what happens in the Euclidean case and what happens in the Heisenberg Group case. Okay. So there is this modulus inequality, which in its most general has been proved by Fouglede, but the proof for the Heisenberg group, you can find it in the works of Ballon, Fassler, and myself. And it goes like this. If you have a K quasi-conformal mapping between domains and you have a family of horizontal curves, then the modulus of the image family is bounded between K squared of the modulus of gamma and 1 over K squared of the modulus of gamma. Compared to what happens to the Euclidean case, you don't have squares in K. You just have K. Here, this square always appears. So this is the geometric definition based on this modulus inequality. It's quasi-conformal whenever for every curve family you have that modulus inequality holds. Okay? So, before I go into the final thing in these definitions, I'm going to talk about the definition of a quasi-symmetric mapping. So a locally H quasi-symmetric mapping, there exists an increasing self-homeomorphism such that for each Whitney ball, this inequality holds. Well, a Whitney ball is just a B such that 2B is inside the domain. Okay? So we have the theorem. The following are equivalent. Quasi-conformal according to the metric definition is locally quasi-symmetric. Quasi-conformal according to the geometric definition. Okay? All definitions are equivalent. So that was the start of the Koranyi-Reimann theory for the quasi-conformal mappings of the Heisenberg group. Basically, it is one paper back of 1985 or so in Inversiones Mathematica. Okay, so we have a very, very important thing here. If we want to have quasi-conformal mappings in the Heisenberg group with sufficient smoothness, then they have to be contact. This does not, nothing similar holds in the Euclidean case. Okay? It's a distinguished. It's what distinguishes quasi-conformal mappings of the Heisenberg group from the usual quasi-conformal mappings. So PD theomorphic K quasi-conformal mappings are just contact transformations with this property. This is a theorem of Pansy. And the converse is also true. You have a C2 contact transformation which satisfies this condition, then it is K quasi-conformal. So you cannot escape the contact conditions. You cannot do that. But you don't have only a bad side, you have a good side. And the good side is that in the Beltrami system, the second equation is implied by the first. So the Beltrami system is reduced to a Beltrami equation. And a nice Beltrami equation, the first one. All right. Okay, so we have a problem here, and we have something very nice. The problem is that we don't have existence theorem for the solution of the Beltrami equation. And according to Riemann, we have been talked a lot, even if we do have one, we might have one. But even if we do have one, the constraints will be so bad that it won't be handy at all. It won't be useful. But we have a measurable Riemann mapping theorem, exactly as in Alfors-Behr's theory. And perhaps this is one of the most striking results in the original works of Koranyi-Reimann. Okay, so we have a one-parameter group of transformations, Fs, with infinitesimal generator V, which satisfies an initial condition. Okay? Have this theorem due to Lieberman that says that vector fields of this form, and only this form, generate local one-parameter groups of contact transformations. So contact transformations are generated by vector fields that are only of this form. And you see, it is important, this P guy here, which is an arbitrary real-valued function. Take any arbitrary real-valued function, calculate this vector field, calculate the flow, there you are. You have contact transformations. This is an old theorem of Paulette-Lieberman. Okay? So Koranyi-Reimann took this one step further with this theorem. Suppose that we have a vector field which is C2 and generates a one-parameter group of contact transformations. I told you before you cannot escape contact. If you have this bound on the second z derivative of P, then you know that your transformations are K quasi-conformal and the constant of quasi-conformality satisfies this beautiful inequality. So this is the counterpart of the Riemann measurable mapping theorem. And also another consequence is that from this we can produce as many quasi-conformal transformations as we like. Just take a P, right? Then you can construct contact transformations, and if you are lucky so that this inequality holds, there you are. Okay? Not bad. Okay? And I have told that it's the infinitesimal analog of the measurable Riemann mapping theorem of Alfors and Beers in the Heisenberg setting. There is no solution to the Beltrami system. There's no existence theorem, or if you want, there is no nice existence theorem, to my knowledge. But our Riemann measurable mapping theorem is the key step to pass from quasi-conformal deformations of the Heisenberg group into quasi-conformal deformations of the complex hyperbolic plane. Because if you have such a thing, a quasi-conformal deformation of the Heisenberg group, then Koranyi and Reimann have proved that you can extend it into the interior. So this is serious. Okay, that's about the theory, more or less. There are lots of other things, but I think that this covers an introduction. So some developments, and the first one is, to my personal flavor, about extremal quasi-conformal mappings. In the classical theory, these are the ones who minimize the maximal distortion, which is the constant of quasi-conformality, within a certain class of mappings in the complex plane or between Riemann surfaces. There are huge work about that. Teich, Miller, who else? I don't know. I mean, many others. Okay? The first method to study this problem was what is called the Modulus Method. Okay? It is a simple method, very elementary, but it was the first, and there is a book about this Modulus Method in the classical case written by Vasiliev. Okay? Anybody who is interested, he can look at this book. It's a very nice book. Okay, so in this setting, me, Zoltan Balog, and Katrin Fassler have made something similar, have constructed the Modulus Method, have discovered the Modulus Method to find solution to extremal problems, but not of the classical sort. We weren't able to find minimizers of the maximal distortion, but rather we found minimizers of a mean distortion functional. So what is a mean distortion functional? So let us have a domain in the Heisenberg group. Now, let me make a comment here. In the classical case, when we are in the complex plane and we have a domain, say we have a condenser, something that has a hole inside, then applying a holomorphic map, we can suppose that this is the annulus. Nothing of this sort holds here. Every domain is of its own kind. and you cannot move conformally, you don't have so many conformal mappings to move from any domain to some fixed domain. Things are very restricted here. There is no Riemann mapping theorem because there is no holomorphic mappings. There are too many holomorphic mappings. Okay, so suppose that we have a density which corresponds to the geometry of omega. Then the mean distortion functional is this thing. Is an integral of k squared times rho to the fourth power over the integral over the modulus, say. Right? So there is a theorem that we had with Zoltan and Katrin. We had families of quasi-conformal mappings of the Koranyi ring, have Koranyi spheres. The Koranyi ring is bounded by Koranyi spheres, centered at the origin. And for some rho, a certain rho, which is, it's not some random one, but it's fixed, the unique minimizer is an extension of the usual stretch map we have in the complex plane into the Heisenberg setting. The stretch map, of course, this is what it is in the complex plane. In the Heisenberg group, if you try to write it in Heisenberg coordinates, it will be a nightmare, a real nightmare. But we were lucky to use some coordinates that me and John Parker have discussed about for a completely different setting. And with these ones, we tried to construct, we managed to construct a lot of quasi-conformal mappings and eventually solve this problem. Now, how about the minimizer of the maximal distortion? Don't know. It's still open and it does not look good. It does not look easy at all. Okay, so let's go to another area. Extremal problems arise in the theory of quasi-conformal mappings of compact pseudo-convex CR manifolds. I don't want to get into the details of that, but there is a starting paper of Koranyi-Reimann about that, and then there were people like Robert Miner and Puki Tang that they have written very nice papers about the theory of these things, of extremal problems into CR manifolds. So the problem can be stated as this. We have two CR structures on a three-dimensional contact manifold, then determine the QC homeomorphisms that have the least maximal distortion with respect to the two CR structures. It's just a generalization of the extremal problem in the Heisenberg setting. The Heisenberg group is a prototype of CR geometry as well. Okay. In abstract spaces, I don't want to get into many details of that, but the study of quasi-conformal mappings in the Heisenberg group motivated the study of quasi-conformal mappings in very abstract spaces. And, you know, in Finland, there is this whole school of Alfors that is studying quasi-conformal mappings in entirely abstract spaces. And they produce a lot of nice results very often. Okay. Abstract spaces, CR manifolds, we talk about CR manifolds. Metric spaces with controlled geometry. That can be Alfors-David spaces or Levner spaces. I don't want to go into the definition of these. Also Carnot groups. And of course Subramanian spaces. Yeah? Okay, so how do we treat these problems here? It's just, the first thing is to show the equivalence of metric definition with some nice analytic definition that we have to produce, and then finding another nice geometric definition and do the Koranyi-Reimann trick of showing the equivalence of metric to the geometric and so on. There is a lot of work that has been done here, and perhaps papers of Tyson, Heinonen, and secondarily Williams are the right reference for that. Okay. Complex hyperbolic quasi-Fuchsian space. To make a long story short, complex hyperbolic quasi-Fuchsian space is the generalization in complex hyperbolic geometry of Teichmüller space, or if you want, the real quasi-Fuchsian space. So, in Teichmüller space, we use all this heavy machinery of Alfors-Behr's theory, the use of extremal quasi-conformal mappings and so on, and we describe completely the Teichmüller space. Can we do this here? Oh, well. So let me give the definition first. So complex hyperbolic quasi-Fuchsian space of a closed surface of genus G, or, well, you can have surface with puncture, but let us remain in the closed case, are representations of the fundamental group into SU21 of complex, which are discrete, faithful, totally loxodromic, and geometrically finite. Okay? I have told you that the Teichmüller space is a counterexample of most rigidity. The conditions of discrete and blah blah prevents the complex hyperbolic quasi-Fuchsian space to fall into the most rigidity setting, because the representations are convex co-compact and not co-compact, as in the assumptions of most rigidity theorem. So it has infinite volume, and then we're okay. The manifolds are of infinite volume. And I explain this in a convex co-compact representation. The quotient of the convex hull of the limit set has finite volume, so it may have infinite funnel ends but no cusps. Thus, the limit set can never be the entire boundary. There is always a region of discontinuity. In particular, for a quasi-Fuchsian or complex hyperbolic quasi-Fuchsian group, the limit set is a topological circle, and there is a domain of discontinuity in the boundary. So we're okay. Right. The quest for the Holy Grail. Examine the analytical structure of complex hyperbolic quasi-Fuchsian space. In case of Teichmüller space, this is carried out via the Alfors-Behr's theory. There is a challenge for any one of you, my friends. Use Koranyi-Reimann theory to obtain similar results. Well, to this direction, one is invited to start from an irreducible representation and to construct quasi-conformal deformations with a starting point to determine exactly the tangent space. Yeah? Very open problem. Widely open. As open as you can imagine. That's all I have to say. Thank you very much.
Do you have questions?
I was very clear.
Then to Professor
Thank you.
Platis.
Thank you very much. Thank you. Thank you, guys. Thank you very much.